we'll start with a physical interpretation of normal modes. These are self-sustained oscillations that occur at specific natural frequencies. The word natural takes the proper technical usage the same as street usage, that it's natural for the body to vibrate at that frequency. It's due to a balance of the internal inertia and stiffness forces. It's not dependent on some kind of external forcing frequency. You can characterize such self-sustained oscillations with a sine function or a cosine function or the exponential complex form. It depends on how complicated the problem is. If it's an undamped problem, as we often use in our normal mode, sometimes the sine functions are sufficient. If you get a general formulation, you typically would need the complex exponential to handle the out-of-phase quantities. I've shown here some normal modes for a cantilever beam. You see a shape involved in each case, and that shape is actually an envelope of a vibration amplitude in which the points on the body would move back and forth harmonically. A beam, for instance, moves normal to its initial axis. The second mode would likewise look something like this when you plot the envelope, and the third mode something like that. Now the mode shape and the frequency go together. There will be here a certain frequency, call it omega 1, and a mode shape which we later will call phi 1 of x. Here there would be a second frequency, omega 2, a third frequency, omega 3. Now the mode shapes and the frequencies depend on the geometry of the problem, the materials, the boundary conditions, and perhaps other conditions. You may have under the geometry category, you might have wrinkles or darts and pleats and all kinds of stiffening tricks that people use on sheet metal, or you might have added masses somewhere that would slow the system down. I'm going to show you a physical example in the video inset before the next figure. A few minutes ago I walked out in the consulting areas of automated analysis and swiped a small ruler from one of our consulting engineers. I'm speaking to you from the automated analysis headquarters in Ann Arbor, and we have about 40 people in this building doing all kinds of finite element work. Anyway, here's his ruler, and as you flip the end of it, you see that there's a relatively slow motion here. The frequency that is the natural frequencies depends on how I clamp the end, the material, and then how long this is. Let me show the effect of shortening the length. Notice the frequency is getting a little higher, faster, faster, until now it starts getting into the acoustic range. Let me take shorter and shorter segments. So I think you can tell that the frequency of that beam definitely depends on the length. Let's talk about some other examples. Musicians are well aware of the reeds that are in musical instruments and tuning forks that give certain specific frequencies. In the scientific area, you have crystals and watches, and you have electric devices like electronic counters. Usually there's a quartz crystal, and the useful frequency might have to be found by some frequency reduction and some kind of a division of the frequencies involved. Those quartz crystals have very high natural frequencies, perhaps hundreds of kilohertz. Large buildings like the Empire State Building have a fundamental mode in which the upper stories move through a rather large motion. Large in the sense of perhaps a half a foot or a foot. Small in terms of the total scale of the building, but that's still sufficient to make some people a little bit seasick up at the top of the structure. Then there are window panes and other objects around us. In fact, I used to have a demonstration in my vibration classes where I would bring in a Bentley proximeter and an oscilloscope, and by putting aluminum foil on various surfaces around the room, you could prove that everything around us is moving at all times. Window panes, doors, desks, lights, everything is sitting in a constant state of motion. The amplitudes tended to range from a half of a thousandth of an inch peak to peak down to a tenth of a thousandth peak to peak, but very measurable, each one typically vibrating in a fundamental mode. So normal modes are around us all the time, and there are even some human modes such as that, such as the twitter of the human eye as it observes something. The eye gathers information partly by bright and dark areas having a boundary, and then the eye, by vibrating, will have some of the rods and cones that are going from light to dark, or red to green, and that helps the eye define that area. Okay, the mathematics of the normal mode problem are generally studied with real eigenvalue analysis. That's what we're going to do by neglecting damping. But it is possible to go into complex eigenvalue analysis as well. There you might put damping back in. You might add fluids that cause out-of-phase forces that have the appearance of damping, inertia, stiffness even. You can have gyroscopic and Coriolis forces, and then in more recent times artificial control of structures is starting to add forces that might be out of phase with the dominant displacement. The terminology in the eigenvalue problem is interesting. The German word for eigenvalue is Eigenwerte, and the American equivalent or English equivalent really should be characteristic value. But to give it a little bit of a nice flair, we use one German word and one English word, so we call it eigenvalue. Other cross-use of terms that I've picked up over my career is that what we once called natural modes, we now call normal modes. And the word free vibration can really mean one of two things: either the undiminished normal modes themselves, that motion that continues with time, or the response to initial conditions. In other words, a transient problem that has no loading on it so that it's free. But the thing that's not clear if this is standing alone is whether there are damping forces and whether this is really a response to initial conditions, or is it the continuing motion, the so-called normal mode motion. But I think from the context, people tell what is meant by free vibration. Now, the normal modes and natural frequencies are helpful in structural mechanics in two ways. One way is a pure characterization of the structure itself, because they do give you some feeling about the ratio of stiffness to mass of the system. The first frequency in particular tells you a little bit about that overall system behavior. And then the shape tells you something about the way that the system is likely to move most easily. So when you know the first few natural frequencies and normal modes of a structure, you're already on the way toward defining the behavior of that structure. This becomes less true when you have really complex bodies like an automobile, and it's not sufficient to understand the first 3 or 4 modes, but rather you need to get up higher into the mode spectrum to really see what's going on. One of the reasons is that there are more localized effects, maybe something in the suspension that vibrates, and that might be the 12th or 23rd mode. The advent of interest in quieting vehicles brings in acoustics, and then some of those modes are substantially higher in the spectrum as well. But in any event, bottom line is, if you knew the bottom 100 or so normal modes of a structure and the corresponding frequencies, you'd have a pretty good idea of what that structure was. Now, those modes are not just used for understanding. They're used in a practical way as a working tool, typically in a series approach, so as to expand a candidate solution to a response problem as a series of normal modes. more often it's the spatial part of the problem there that's helpful. In other words, the mode shapes are used quite often. Because if this were a frequency response problem, let's say, then the frequency might more likely be determined by the external force field. Now, nevertheless, both the mode shapes and the frequencies can appear in these response problems. I like to give a geometric interpretation of the eigenvalue problem because it builds intuition and it helps people remember a little of the detail. There really are two eigenvalue problems I want to consider, and one is called the special eigenvalue problem and the other is called the general eigenvalue problem. Let's start with the special problem where you're given a matrix A and the question is there a direction x in the space which the matrix A will map the vector x back into a collinear version of itself, possibly multiplied by a scale factor. So, generally speaking, the matrix A will rotate the vector and either stretch or shrink it. This time we're asking, is there a special direction in which there is no rotation? And so over here on the sketch, I show the original trial vector, a black arrow, and the vector x direction in 2 dimensions. You might think of these dimensions now as being displacements in a body, perhaps u1 and u2. And then the question is there such a preferred or characteristic direction that ax would lie collinear with x as shown? Now in that case, you can see that ax is larger than x, and therefore this lambda value would have a number greater than 1. Lambda is, of course, the eigenvalue. Now, if A is a nice enough matrix, you will find 2 such directions in a 2-dimensional space, so that there are 2 characteristic directions, or eigenvectors. And if A is nice enough, then sometimes those are orthogonal in the physical space. And there are other kinds of orthogonality that we'll discuss later as well. Now the general eigenvalue problem is a little bit different. The question is, given A and B, 2 matrices, does the matrix A rotate a trial vector the same amount as B rotates that trial vector? And if so, then find a scale factor or an eigenvalue that will bring this equation into balance. So over here the question is, with this trial direction x, when ax rotates it this far and seems to expand it just slightly, then the bx rotates farther, at the same rotation but expands it more, then apparently we can satisfy that equation. So it's a little different philosophy because the original physical direction here, or the physical vector, doesn't appear alone in the final answer, but rather has been mapped twice into some new pair of vectors. And you see in the vibration problem then, this is like the displacement vector, and these are like perhaps the inertia forces and the stiffness forces here on the left, and those must align. In this figure, I'd like to combine the terms in a little different way than our geometric interpretation earlier. For instance, in this general eigenvalue problem here, I've put the 2 operators on the left side along with the eigenvalue. Now the question becomes, can this general operator here map a vector into the 0 vector? So this is a nulling operation. We could broaden our definition of the eigenvalue problem to be this set of terms, mathematically a constant term, a linear term, and a quadratic term, and ask that same question. I like to include this because this is often relevant for the damped vibration problem or the problem with Coriolis effects and macroscopic effects and so on. Let me put down the structural notation in this pair of equations where we would recognize this, what was once an A matrix up here is really the stiffness matrix, and then the matrix that has the eigenvalue appearing is the mass matrix. Phi is the symbol given for the eigenvector when you've taken the time dependence out. So these are generally spatial terms that are displacements of the structure at nodes in our case. But again, asking whether this combined matrix, sometimes called the dynamical matrix, will map the proposed set of displacements here into the zero vector. Then we can generalize that into the problem that has not only stiffness and mass, but also damping terms. All of these above equations fall in the form of a dynamical matrix times a proposed answer being mapped into the null vector. And I think this interpretation has an advantage in some special cases. There's times when you try to drive error to zero, and you might think of this vector on the right-hand side as an error vector, which you would like to be zero, and you might find methods that work on that and try to drive it to zero. These would be approximate methods or iterative methods. In the classical study of differential equations and integral equations, Fredholm used to distinguish between different kinds of solution types. Those were called the four Fredholm alternatives. I like to use that same idea here in our matrix problem. You have perhaps a problem in this form, and right now I'm thinking of it as a linear set of equations that are algebraic. In other words, a matrix linear algebraic problem. The dynamical matrix here would map the displacement vector into another vector over here. We might think of the y as the forcing function on the problem, and then x as the response. The four permutations result from the fact that either the determinant of the coefficients of that dynamical matrix are zero or they are not. And likewise, either there is an external force present or there is not over on this side. So the four combinations are found by taking one of the two alternatives on the left, one of the two alternatives on the right. Now, the one that we're interested in today is called the eigenvalue problem, and that's where you have the determinant of the matrix equal to zero, and there's no external force on the system. Another possibility would be the determinant to be zero, but there would actually be a force on it. Now that's pathological because your determinant of this matrix being zero says that there's a singularity, and in our terms that means there's a kind of displacement field that has no natural resistance to motion. In the dynamic sense, that's a normal mode, and if you put a force field on the system that tries to excite that kind of motion, you'll get a singular answer. So we generally try not to solve this problem in this class. There's only one application I know where this pathological case is of interest, and that's in the sensitivities for eigenvectors. But that's very high-level work. Now the other two alternatives come when the structure is a conventional stable structure, and either there's no load on it, in which case you get the trivial solution that there's no displacement, or there is a load on it, in which case you get the standard stress or response problem. The interesting one that we're interested in is this eigenvalue problem where the matrix has seemingly some weaknesses in some displacement directions, but there's no force on the system. And so you really have the opposite of an irresistible force meeting an immovable object, because now we have a system that's incredibly weak in certain displacement patterns, but you don't have any force on it, and so it's going to vibrate on its own without any external force in those so-called weak directions. I'm going to do a numerical example just to get us into the mathematics of the eigenvalue problem. I'm going to pick a clamp beam shown here and model it with two finite elements. We'll make some assumptions on the problem, namely that this is a slender bar and has a square which is a compact cross-section. That means that the Euler-Bernoulli theory will apply. It's constrained to move only up and down in the xy plane, so I'm not interested in torsional and axial motion nor bending out of that plane in the xz direction. The resulting motion will be what I'm going to call pure flexural motion. Let's suppose that our goal is to find the first two natural frequencies and their corresponding mode shapes for this flexure in the xy plane. The accuracy of those two modes would be in question. Rayleigh many years ago said that you needed to have twice as many degrees of freedom in the system as you are going to receive accurate answers for the eigenvalues. And so historically there's always been a tendency then to carry twice as many degrees of freedom as you're interested in engineering accuracy. This problem is going to be a little bit strange in that we can't apply that rule directly because there are going to be 2 degrees of freedom at the left end, 2 at the middle, 2 at the right, and there's a total of 6 degrees of freedom. Yet those degrees of freedom at the boundaries are clamped, and there's some question, are those real degrees of freedom or not? So we'll check that out at the end of the problem and try not to draw too many false conclusions from the answer, because we know that it's a bit hard to interpret in this case. I like to point out the physical modeling ideas first and then follow with finite element modeling. And that has been a practice of mine since talking with Jerry Joseph years ago at McNeil Schwindler, where he said that fully half of his questions from the field in his role as a consultant to the industry had to do with the physical nature of the problem. Was it a beam or was it a plate? In other words, engineering mechanics. So I try to separate out the engineering mechanics from the finite element questions. This beam is slender. As I've drawn it, it's much more than 10:1 aspect ratio of length to height. We'll neglect any damping. We won't include any external forces. Clearly, it's a clamp boundary condition at each end, which will constrain both rotations and translations there. And the deflection that we're interested in, we will label v of x. So this is a deflection in the y coordinate, and it's a deflection of the neutral axis. Our finite element model now, as we go into finite element approximations, is a 2-element model. There will be both a translation and a rotation at each of the 3 nodes. There is no axial motion implied, which would be a column action. We're interested only in this lateral flexure. The mass matrix we worked out in an earlier lecture, and our stiffness matrix came from earlier work in linear static finite element theory. I'm going to be free to put in the boundary conditions at the left and the right end, specifying 0 acceleration there and 0 displacement there. Those are the points where I don't know what the reaction forces are. I'm going to follow a convention that I've used in my engineering teaching with mechanical engineers and aerospace engineers, that I'm going to put live loads and reaction loads together in this vector on the right side. These are the reaction forces actually above and below at the fixed degrees of freedom, and then these 2 locations would be where the live loads would have been applied had we wanted them. Civil engineers are a little more careful in their bookkeeping and often have 2 vectors where they separate out the live loads and the reaction loads. But I think in most mechanical engineering problems and aerospace and many other fields, putting those together does not do a disservice, and it's easy to uncouple those ideas. So We know that when you post-multiply a matrix by a vector, that these zeros tend to cancel columns in the matrix, and so you might as well cancel those terms and forget them in any resulting multiplications. Secondly, since there are no unknowns in these locations, we will partition out the remaining equations. The first equation, the second equation are merely set aside. And with these zero terms here, there's no coupling then between those two equations that prevents us from solving. There is some coupling in a one-way direction that maybe we can discuss later. So basically, by partitioning out the first, second, fifth, and sixth equations, you're left with relations that involve this interior set of terms. And those are repeated on the next page. So reaching back into earlier lecture material, we have the actual symbolic terms shown here. We're left with the accelerations at the interior node that has 2 degrees of freedom and the displacements at that interior node. This is a bit of a special problem because of symmetry, and we find a fortuitous simplification that these off-diagonal terms cancel there and there. The way that I would say then to discuss this situation is that there is inertial uncoupling here, and lo and behold, the same thing happens on the elastic coupling terms, that this term vanishes as well as this one. Now that's unusual. It's helpful here because it simplifies the math, but it's not the general case. More generally, your degrees of freedom that you've chosen, which are physical degrees of freedom at nodes, would be coupled to each other in all ways, inertially and elastically. But the simplified equation that we get is shown below here. Some of you might recognize then that these equations directly uncouple and they could be solved as 2 standalone scalar equations, but I want to carry along the matrix concept. So the zeros appear and we've done some collection of terms and a bit of simplification. We have now a set of linear, ordinary differential equations in time. There are 2 variables. We might change this from a second-order differential equation into an equation of constant coefficients by assuming harmonic motion. And this effectively removes the time variable. We do that by assuming that those interior coordinates move harmonically with this complex exponential behavior. Then phi3 and phi4, where the indices are inside the vector symbol, mean that these are components phi3 and phi4 in degrees of freedom 3 and 4. I put that expression into the differential equation, and you find that the derivatives on time bring out this I omega squared quantity. We're left with the e to the I omega t as a common factor, and we don't want to let that cause the equation to be brought into balance. We want this equation rather to be true for all time. So we just cancel that term and don't allow it to zero out the left side. Then we collect terms shown below here and start collecting the important frequency-dependent terms in this quantity, which we'll call the eigenvalue. In the next figure, I will do a bit more of consolidation and handling these coefficients and simplifying them. We will do the simplification of the equations by dividing out constants in a way to make the mass matrix simple. You have a bit of a choice. Do you want the stiffness matrix to be really simple or the mass? And often it's done in this way. Here we're able to put units on the main diagonal, which is a kind of a standard way to scale a problem. The frequency content is involved in this eigenvalue. The displacement field that's proposed is here. This would correspond to the static values that define the envelope of the normal mode. The real question is whether you can bring this system into balance or not. And so we have that second form of the problem where we emphasize that there was a dynamical matrix attempting to map a proposed vector into the zero vector. Now, we can put the terms together because matrix addition can be handled this way, and see that on the main diagonals there are terms that have both inertia and structural stiffness properties in them. Again, we're still asking, is there a dynamical, for this dynamical matrix here, is there a direction here that can be mapped into zero? Now, the only parameter you have to adjust is the eigenvalue lambda. And when you pick a value of lambda as a candidate eigenvalue, you have to put it into both equations, because this is a set of equations that must be satisfied for whatever mode, shape, and frequency that you arrive at. Now, there will be more than one answer, which is the interesting thing and makes this different from the common response problem. Not only are there more than one answer, but there are two classes of answers here, and one of which is the trivial class of answer where we just take the displacement field to be zero, and we say that, well, this matrix will map 0 into 0 at any frequency you'd like. Well, that's not too much fun. That's like kissing your sister. So, although this is important to know, it's not useful. The other class of possible solutions, which has subcase solutions within it, is that the determinant of the matrix is 0, but that now the phi vector has to take a certain peculiar characteristic direction to satisfy the problem. And of course, that's the normal mode that we're looking for. I like to use the word shape because many people, when they first look at this problem, just don't get it, that this phi is a matrix of displacements throughout the body that helps define the envelope of vibration. And these are constants, but they are actually amplitudes of the vibration that tell the shape in which the structure is vibrating. The condition for a set of linear algebraic equations to have a solution when there's a zero right-hand side is that the determinant of the coefficients of the matrix must be 0. Now, that determinant in our case would be the diagonal terms times each other minus the off-diagonal terms. Those are 0, so you get this simple expression. This is already in a factorized form. There is no need to go further. We immediately see that if lambda takes either the value 32 here or the value 420 here, that you will satisfy the balance of forces. I've had students in my exams, in particular in the past, that will find this characteristic equation, we'll multiply it out, and then we'll use the quadratic formula to find what the roots are. And they don't understand that when you've already factorized equation, that's already it. Those are those zero crossings of that function, if you think of this as a function of lambda, are already given to you when it's factorized. But I'd say typically a quarter of the class will do that if they're put under extreme stress. So what you must do is look at these one at a time as candidate solutions. Lambda 1 of 32.3. We go to the equation set here, put the eigenvalue into both locations where it appears, and then ask if there is a phi direction that works. Well, the first equation vanishes, so you don't get any condition on phi 3. In other words, phi 3 is arbitrary. The second equation, however, says that 387 times phi 4 is 0, or in other words, phi 4 has to be 0. So you're left with the interesting solution that at this non-dimensional frequency ratio here, that if you draw a shape as shown where the body oscillates back and forth between these two positions, that if there's no slope, which is phi 4 is a rotational degree of freedom, and this merely translates nicely and symmetrically up and down, that is the so-called first mode of vibration. Let me summarize the results from that first eigenvalue and eigenvector calculation. The eigenvalue here, which was a frequency term basically with frequency squared appearing in it, was 33.2, and we could recover the physical quantities from that, knowing the beam properties. Here you have the eigenvector, which is the shape. And rather than take an arbitrary amplitude for phi3 up above, I'm taking a unit value, and that's often done to scale the eigenvector such that it has a unit value in its largest coordinate. The one that appears outside these curly braces shows that this is the first eigenvector. It does, of course, have two components inside the braces. Now you find the second eigenvalue the same way. The number that we found from the so-called characteristic equation or characteristic polynomial that was factorized was 420. So we put 420 back into the combined equations. Interestingly, this time it says that phi4 has no condition on it since the equation results in 0 equals 0. So this component down here, shown in normalized form, really is arbitrary in size. The first equation, though, said that phi3 had to be 0, and so that appears here. Now this is then the second eigenvector with the two appearing outside the curly braces, and it looks like this figure here. Now again, this is just the envelope of the kind of motion that would occur, and so you have to think about the motion moving up and down between those limiting positions. Now I'd like to compare our answer with classical theory. Here's the general expression for the eigenvalue. It's really a definition. I'll carry a subscript I on it as well as on the natural frequency so that it can either be the first or second eigenvalue. Rho is the density of the material of the beam. A is the cross-sectional area. L is a little bit of a trick, that it was the length of our finite element, which is really only half the beam length. So as I move into the comparison with theory, I need to change over to a length that's the full beam length, L tilde. E and I are the Young's modulus and then the moment of inertia of the beam about its neutral axis. Now we found these non-dimensional numerical numbers here that are represent this frequency, so-called frequency ratio that I've been calling it. And we can recover specific frequencies out of this or even leave it in symbolic form, which can occur by putting this lambda in here. And when you do that, and if you bring that square root of lambda out, you get what Thomson calls a k value by properly handling this. And you found that our finite element number here corresponds to this number that's a textbook classical value, and we're only 1% different. On the other hand, the second eigenvalue is substantially higher than the textbook value by 33% roughly. So according to Rayleigh's original idea, by carrying these two active degrees of freedom in the interior of the beam, we seem to have gotten, in this case, one answer to within engineering accuracy and one not. But I think the question of how you handle in that approximate idea the end degrees of freedom is not clear. So I tried not to emphasize this rule as a hard and fast rule, but kind of an engineering aid. Let's discuss our results. It will turn out that the mass and stiffness matrices that we've used are nice ones, and that our answers give eigenvectors that are orthogonal in a certain sense. Now, it's not in the common Euclidean sense that they are perpendicular to each other necessarily in general, but rather that they are orthogonal with respect to the mass and the stiffness matrices. So this result shown here is a general result that would happen in all such vibration problems that are of this normal mode type with no damping and with nice mass and stiffness properties. The fact that you could take one of the eigenvectors and pre-multiply the mass matrix and then post-multiply by the other eigenvector in our problem, and this time this triple product is really a scalar triple product and gives you literally the number 0, provided you use different eigenvectors, then this is orthogonality with respect to the mass matrix. The same thing happens here with respect to the stiffness matrix. You pre and post multiply in that triple product, you get the number 0. And this is general. This will happen in a broad range of so-called self-adjoint eigenvalue problems where you get nice eigenvectors. Now notice this is a condition on the shape in which the problem must vibrate. So in our case it was a cantilever beam. And basically it says that the two vibration modes that we have found are as different as possible from each other. We can check whether it holds in our case by just substituting our answers. Here was our phi1 was a translational degree of freedom at that center node, and this was the first mode. On the other hand, phi2 was this one here, was the second mode with a rotation at the center node. The mass matrix that we were able to simplify was the identity matrix. You multiply those two, well, what I'm saying here is you first multiply these two to give the second vector, and then you pre-multiply and get the 0 quantity. So that checks this orthogonality with respect to the mass matrix. Now the second condition on stiffness also holds. These numbers are not quite as obvious now. You do the multiplication on the back 2, and you get 0 and 420. But in this case, because of the special nature of our uncoupled problem, this easily comes out to be 0. So we have proven that there is orthogonality with respect to the stiffness matrix. In addition to the orthogonality that we just discussed, there's another kind of handling of the vectors that's important, and that's called the creation of orthonormal modes. Now this is a scaling of the modes such that they have a certain prescribed inertia content. And it's done in reference to this equation where you have a triple scalar product with the mass weighting. And so by putting the same eigenvector in the first location and in the third, you're getting an idea of the size of this vector phi as modified by the inertia of the system. Now if you pick that to equal 1 when you put the same vector on either side, then you get this option over here. We already showed that in general you do get a 0. In other words, the modes are orthogonal with respect to the mass matrix when you put different modes in these two sides. So they're orthogonal to each other. So now what we're talking about now though is normalizing the vector phi and using a different scale factor than the one that we used previously where we had a maximum unit value in any of the coordinates. So this kind of normalization leads to so-called orthonormal modes. The notation's a little tricky because now the orthogonal part comes under ortho, and this normal means normalized size with respect to these inertial properties. Now it will turn out that we have gotten this kind of normalization in the sense of scaling of the vector automatically just due to luck, and that the two kinds of scaling of the vector, either using a maximum size of 1 or doing this mass normalization, give the same answer here. So here's our first eigenvector on both sides. You multiply that out. Typically I do the second multiplication first, giving this vector, and then that comes out unity. Likewise with the second mode shape, with the scaling that we had picked for other reasons, 0, 1 in fact, you do the multiplication, you come out with unity again. So the conclusion is that our modes are orthonormal, and we just lucked out because of the scaling way that we scaled the vector with unit maximum size. Also gives you the mass property that we desired. Often it's important to get an estimate of the dominant eigenvalue in a problem. This can be done by a method called Rayleigh's quotient. It starts out with the general eigenvalue problem in this form, and usually the physical problem determines the matrix A and B. Then, if we presume that we can guess the shape in which the body vibrates, we can put that in as an approximate known quantity. That leads to a set of n equations here below, which have really only one unknown, namely the eigenvalue estimate. So one way to convert this into a single equation in the unknown is to pre-multiply by the vector itself. I've heard some people call this a Galerkin approach. The effect of pre-multiplying by the displacement vector means that you're changing a force balance into an energy balance. Here's the resulting equation, and you get these quadratic forms on the left and right side. These become what I'm often calling a matrix triple product here. It's a number, and this one here is a number. So when you solve for lambda, you really have the ratio of two numbers. And basically this is a ratio of the stiffness energy or the strain energy in this system compared to the kinetic energy. This is a way that is used to get an estimate for the fundamental frequency in a structure, and you need to be able to predict then the shape of that fundamental mode. That's not too hard on something like a cantilever beam, and the Rayleigh quotient will come moderately close to giving the eigenvalue in that case. Now, the special eigenvalue problem that we also discussed is just missing this matrix here, the B matrix, and so the Rayleigh's quotient just simplifies a bit. Often, because this is most accurate when it's used in studying the first mode, it is understood that the Rayleigh's quotient will be used for the fundamental mode. A matrix consists of many terms, and sometimes it's difficult to tell something about the good behavior of that matrix. Many things like strain energy, kinetic energy have to be positive, and so the real question is, would that matrix in question cause physically realizable quantities? For that reason, the term positive definite has been invented to cover a situation where this triple product formed here is always greater than 0 for any trial vector x. If this were, for instance, a strain energy calculation, A would be the stiffness matrix and x would be the displacement field. And the question would be, would you get positive strain energy for every conceivable displacement of the body? If this were a mass matrix, then x might be the velocity field, and the same thing would come up with kinetic energy. The fact that this is strictly greater than 0 means that you cannot get 0 energies. That has quite an impact on rigid body motion, which is of a second category. If you had a system that had rigid body modes in it, then you would say that the stiffness matrix were positive semi-definite, as shown here. This means that there could be some displacement fields that would create no strain energy. For mathematical completeness, people often define negative definite and negative semi-definite This is kind of academic because it's more common than to put a minus sign on the matrix and discuss it in terms of positive definiteness and semi-definiteness. In structural vibrations and in physics, in various fields, there has developed a notation that's somewhat universal. The eigenvalues themselves are often aligned as along the real number line if they're real eigenvalues, and they are called the spectrum of eigenvalues for the system. So if someone speaks of spectrum, you have the idea of all these eigenvalues side by side. Of course, this is true in physics with the color spectrum found by shining white light through a prism. The eigenvectors themselves can be lined up in a similar way, and normally you would associate one of those with each of the eigenvalues in the spectrum. Sometimes the symbols are grouped in a matrix form to help on some operation, and this lambda here is a diagonal matrix, often with a capital lambda, made up from the individual eigenvalues arrayed down the main diagonal. The modal matrix here is often written in column form with the first, second, and so on lined within as shown. I've seen authors try to do that row-wise, and it causes all kinds of problems because the world pretty much is oriented column-wise on such displays. Also, the way that computers work, they often treat variables in a column-wise fashion, so you can slow down a numerical process depending how you do your matrix multiplications if you're not careful. Our first problem in the problem session is going to be a system that I've simplified until the point where it's a single degree of freedom system. The question is whether you can find the first natural frequency for a beam of length L that's clamped at the left end and is guided at the right end. This is a roller skate condition where the slope is not allowed to change. In other words, this body will vibrate up to this position and then down to this position where the slope is 0 at the wall on the right. We're only going to use one finite element in our solution of this problem, just as an academic solution, and it will let us get a quick measure on the first mode of the system. Even though we start out with 4 degrees of freedom, there's only one active degree of freedom that remains after we apply the boundary conditions. Here's our finite element model with 2 degrees of freedom at each end. This is treated as an Euler-Bernoulli beam. I'm not interested in axial motion, nor torsional, nor out-of-plane flexure. So there are the 2 degrees of freedom at each end of the beam. Now the clamp at the left will knock out the first and second degrees of freedom, and the guided condition on the right will knock out the rotation U4. If you assemble a single beam element, then you get these matrices, the mass and the stiffness matrices. The red lines show the columns that are crossed out because it's a trivial multiplication. That would reduce this set of equations to a set with rectangular matrices. Actually, a matrix that only needed terms here that are 4 rows times 1 column, and then the only unknown being U3. This would give you 4 equations and 4 unknowns, and then you would want to partition out the first, second, and fourth equations and set them aside to find reactions later. The third equation can be uncoupled and solved for the unknown displacement amplitude U3. So that equation is set aside here. It's currently a second order ordinary differential equation. We reduce it to an algebraic form by assuming harmonic motion in time, and that complex exponential appears again then in both terms and can be canceled. It also brings out a minus omega squared, which to our view is the eigenvalue in the problem. Now this could have a trivial solution of no displacement at any frequency, or it could have a non-trivial displacement but at exactly only one frequency, namely omega squared equal to this set of parameters. Notice that you bring in the material properties of Young's modulus and material density. Then you have the cross-sectional moment of inertia, the area of the beam, and the length of the beam. And the length appears here as well. You solve for frequency, and this is our approximate solution. Now we know that the mode shape is being characterized only by 4 shape functions. These are cubics, and we realize that our assumed displacement field here as the limiting envelope of this pattern of vibration is not the exact one. Nevertheless, we're within 4.4% of the correct answer. Now we started out with 4 degrees of freedom, and we constrained 3 of those in the boundary conditions, leaving 1 active degree of freedom. Now whether that makes Rayleigh happy or not, I'm not certain. We got 1 frequency to engineering accuracy in this problem. And there's a question of whether there were really 1 active degree of freedom or whether all 4 degrees of freedom were helpful. So I think I'm going to beg the question on whether Rayleigh is happy or not with this particular solution. The number of degrees of freedom in here I have seen and the accuracy corresponding thereof to wander on these very small problems like this. When you get to larger problems, it's clear that you need to carry at least twice as many degrees of freedom, and people usually overkill and carry many, many times more than twice the number of degrees of freedom. So although I've mentioned Rayleigh's rule of thumb, it turns out in practice in industry, the real problem is cutting down the size of your model size in finite elements and getting it down to a low enough number of degrees of freedom. We've used the beam element for several examples of natural frequency, so our second problem will have a triangle as an example. This is a plane stress, constant strain, equilateral triangle. Sometimes I call it the Turner triangle. It's made of aluminum, it's clamped at the bottom edge, and then the question is, what are the natural frequencies of a body modeled with just 1 element? Now, we know that by clamping the bottom edge, we're taking out the degrees of freedom normally associated with the base, and so basically we're going to have the tip vibrating, and there will be some question whether it moves horizontally or vertically. The description of the problem is given in detail here in metric measure. I will give the shear modulus because it appears later on in the one kind of motion. Let's write out the equations of motion for this triangle. The general form of the equation is mass times acceleration plus stiffness times displacement equals the external force field. We're going to set that equal to 0 because we want to do the eigenvalue problem. And when we do that, we get this general set of equations below. With a single element model, we have 6 degrees of freedom, and those degrees at the first and second nodes here are going to be set 0 as shown in these terms on acceleration and these terms on displacement. As before, we can cancel out columns that are multiplied by the zeros, which gets rid of the first 4 columns in each matrix. And then we can partition ultimately the first 4 equations out, leaving the last 2 equations. And the terms of interest then lie on this square block that I'm outlining. Now, I'm presuming that you can find the mass matrix for the triangle in my earlier lecture in this series, and you can find the Turner triangle stiffness in the linear static lecture series or some textbook. What you find is, interestingly, for the elastic part of the Turner triangle, when it's clamped like this, that one of the stiffness terms is primarily a stretching stiffness here, the EH term. The other one's primarily a shearing kind of stiffness, and those act on the 5 and 6 coordinate directions. I've picked this Turner triangle with a little bit of malice aforethought because I know that it uncouples and you get the vertical and horizontal motion at that tip to act independently. The way we say that in mathematics is that the equations uncouple. The equation for U5, which is the horizontal motion of the tip, involves the inertia term and a shearing stiffness term. That one I have plotted below here, and it's primarily the tip of the little element tipping as shown. Now actually it moves with straight-sided motion because the Turner triangle is required to do that, but I've drawn it in kind of with artistic license here as if it were a freestanding element. In the case that we look at the first equation as a non-trivial solution for U5, but set U6 to be 0, then we're going to get this mode and this frequency. Let's put in numerical values and find out what that frequency really is. And for the given aluminum triangle, we find that the frequency is awfully high. We have here that it comes out after putting the numbers in at 14,000 hertz. So this body is relatively stiff in regard to the shearing motion. It is a thin sheet, and sheet material is relatively stiff within its own plane. Even a piece of paper, you know, is pretty hard to stretch very much or shear, although you can bend it out of its plane rather easily. But there is reason to believe that these high frequencies are okay. Now the second eigenvalue comes from the alternate solution where we take the coordinate U5 to be 0 and let U6 be non-zero. And in that case, we can solve directly from our set of uncoupled equations to find the second natural frequency. As shown in the previous sketch, you can see that this second frequency is extensional, and the tip node at the top of the triangle moves up and down. And putting in the proper physical coefficients for this sheet of aluminum, we get 24,000 hertz for that frequency. So that is certainly a stiff little triangle. Now, the single element model that we have chosen is too stiff in general because we don't give it enough freedom to really deform in a general way. The constant strain triangle was originally developed as if it were embedded in a plate where there were many neighboring elements, and together they often act with straight sides. But we know that for a freestanding single element that more likely there would be some cupping of these sides as I sketched the shearing mode originally, and yet the element is not free to do that. In fact, must move with straight sides. So as Rayleigh showed 100 years ago, when your elastic model is too simple, then you constrain the ways that it can move and your frequencies are too high in general. In our third problem, I'm going to look at a pathological eigenvalue problem. Earlier I had told you that nice eigenvalue problems with n degrees of freedom have n eigenvalues and n corresponding eigenvectors. But that's not always the case, so I thought you should see the counterexample. Consider a general eigenvalue problem shown here where you have this matrix and this matrix as the given quantities. Then the question is there an xy vector that will bring these two matrix forms into balance and give a zero vector as a result? Well, we're used to solving two equations and two unknowns and thinking this happens, but no, it doesn't always happen. And we're going to look at this solution and then explain it and ask, does it make any physical sense? Secondly, what kind of a mechanical system could this system represent? Well, while it's in front of me, I'll point to this matrix here, which would basically be a stiffness type of matrix. And this is a reasonable stiffness matrix, I know from things that we haven't yet discussed. The determinant of the matrix is 2 times 5, which is 10 minus 4, equaling 6. And that's positive, that's fine. The main diagonals are positive. This is, in fact, what is called a positive definite matrix. But over here, this matrix in the mass position is pathological. It has no quantity here on the main diagonal, so there's a massless coordinate, first of all. Secondly, there's an unsymmetric part here on this mass matrix, and that cannot happen in nature. So this is a weird, I'm going to have to put a weird matrix problem over here. And then we'll see what happens next. When a person solves simultaneous sets of linear algebraic equations, the condition for a solution to exist when there's no right-hand force is that the determinant of the coefficients be 0. So that so-called characteristic equation is shown here. The eigenvalue lambda would normally be associated with a frequency in such a vibration problem. Now this is a non-symmetric matrix, first of all, and that's puzzling because it's hard to get those in nature. It can happen in some problems like flutter of wings, some of the non-conservative problems, however. But when I take the determinant here, you get 2 times 5 minus lambda minus 2 times 2 minus lambda, and you multiply that out and you get 6 equals 0. So unless we need to reinvent our whole system of algebraic manipulations, this is impossible. And it means there is no way to cause a balance of forces such as we have proposed. So there are no eigenpairs in this problem, or eigensolutions. The mass matrix is singular and it's non-physical. So the equations make no physical sense. And would there be a system that we could even pose as a hypothetical thing, you know? I don't think so, because to get a non-symmetric mass matrix would fall under the category of what we would have for stiffnesses as a so-called circulatory stiffness. And I don't think there is such a thing as a circulatory mass. Who knows, maybe someone will find one someday, but we are not able to find any eigenvalues and eigenvectors on this problem. Now I'd like to move from single elements up to a system and try one mechanical system and search for its vibrational modes. This will be tougher because there are more variables. I'm going to bring in a side issue, and that's the application of the Buckingham pi theorem, because sometimes it's good to stand back from the problem's numerical aspects and look at the symbolic nature and see if you can understand the number of variables that have to be involved in the solution. This solution is going to involve a beam, a rod, a concentrated mass, and a spring. So we're getting pretty tough here. The concentrated mass is going to dominate the other masses, and that will help us simplify the problem in the inertia matrix. We're going to ask that we find the characteristic equation in the determinant form for these frequencies, and then find the frequencies. Then I want to thoroughly discuss the application of the Buckingham pi theorem to this problem, and show how clusters of physical terms can be bound together and simplify the problem. Here's a sketch of the system that we're discussing. There's a beam that's cantilevered from the left wall and has a point mass at its tip. There's a rod that extends from this grounded position up to the mass, and a linear spring, capital K, that's grounded on the right wall. Since the point mass dominates all the other masses, we won't do any bookkeeping on the other masses. The degrees of freedom that are of interest are shown below. For the beam, there's a possibility of axial motion because of this mass, so we'll keep in the U1 displacement component at the left end as well as U4 at the right end. Then the classical Euler-Bernoulli beam in flexure requires U2, U3, U5, and U6. The rod only acts in tension and compression and only requires U5 at one end and U7 at its base. The linear spring here only requires the horizontal deflection at that wall. So those are our 8 degrees of freedom, and the boundary conditions are going to constrain these 3 at the left wall, this one at the right wall, and this one at the floor. Let me introduce some shorthand for the stiffnesses so that I don't have to carry so many symbols in our matrices. K0 and K1 represent the stiffnesses of the beam at the top, and the symbol 1 means that that's our first element. This is the flexural stiffness term, and then this is the axial stiffness term. K2 over here represents the stiffness of the rod at the bottom of the problem as our second element. And the inertia terms, when they are accounted for, will add in only due to the point mass. We're not going to worry about the beam and rod and spring masses. And the total mass m will act both in the U4 and in the U5 directions and appear as symbols on the main diagonal. This is a lumped mass, and there's no coupling between those 2 degrees of freedom, thereby giving the zeros here and here. Likewise, there's no rotational effect, and so there's no mass on the coordinate U6. We'll assemble the stiffness matrix in a similar manner as we did with the mass matrix. Again, showing rows and columns that won't be of interest crossed out. The degrees of freedom U4, 5, and 6 are the surviving degrees of freedom located at the tip of the cantilever beam at the mass. And you can see how the various stiffnesses add in to oppose the motion of that particular node. We have several stiffnesses that agglomerate together, and they appear in this pattern. Now the first thing we'll do is reduce our original 8 by 8 set of equations to the appropriate 3 by 3. Here is the remaining stiffness matrix and mass matrix, and in these coordinates that survive, and there's no force that's external. We'll assume harmonic motion now, and let us clear out the time variable in the problem. So we'll assume that this is a standing wave sort of motion where there's a spatial part and a time part. Then by taking derivatives, we'll recover a minus omega squared here, acting on a stationary part and then the complex exponential. Here now is our mass matrix, which picks up in a minus omega squared factor, and then these constant coefficients. The stiffness matrix is unchanged, but has the constant terms and again the exponential. Now we can do some non-dimensionalization here to turn this problem into a more tractable form, what we might do is define a new dimensionless set of displacements. That means that we will divide the two translations, U4 and U5, by a characteristic length here, L, and then the rotation, U6, is already non-dimensional. First thing we'll do is cancel out the complex exponential, and that's shown here. We knock out e to the omega t. Now we have dimensionless coordinates involved, and we ought to be able then likewise to convert the coefficients into a dimensionless form. That's done by arbitrarily choosing three dimensionless ratios. At this point, I'm not calling these Buckingham pi terms because we're doing this more from an analytical approach. But here's one that has the mass and frequency in it, so this is basically your eigenvalue. Then there are these stiffness ratios over here. This one even is additive and has two stiffnesses entering. You can see that I'm using K0 as the reference stiffness in all three terms. So now in this pi notation, you have the characteristic equation for a non-trivial solution to be the determinant of this total operator. And there are, in fact, three dimensionless ratios involved in there. So at this point you would say, I ought to be able to solve for one of those variables, such as pi 1, in terms of the other two. And then the question is that logical or not? A formal way to discuss whether you have the proper number of non-dimensional terms is called Buckingham's pi theorem. And this will give you an idea of how many terms are required by the dimensions of the problem. Experimentalists often use this method, but it's also useful for theoreticians. One way to approach would be to approach it blindly if you knew nothing about the physics of beams and rods and point masses and so on. Then you might start out with raw variables shown here, all the variables that enter the problem, and you look at the dimensions involved. Now we know that with our gravitational system that we use force, length, and time, and those are the three independent mechanical dimensions. Had there been a mass term in here, we would, well, there is, in fact, I'll say it that way. There is a mass term, and you have to get rid of the dimension mass by using Newton's law and replace it with force times squared over length. And so now the question is, how many original raw variables did you have? Well, there were 10 such terms. How many independent dimensions were involved? And these were all mechanical dimensions. There were 3. That would leave you 7 terms. And that's the prediction of the Buckingham pi theorem if you don't use some insight into the problem. We'll use some of our analytical knowledge that we've gotten in setting up the actual equations of motion to do this Buckingham pi argument. We know that mass and frequency only occur in that combination. We know that the stiffness of the axial portion of the beam element only has this characteristic. The axial component of the rod has this set of terms acting together, and then the bending stiffness of the beam acts only with these terms. And when you look at that, you find that they're all force over length. Now, if you think of it in that way, the only independent dimension really is this ratio of F over L, and viewed in this new way, the Buckingham pi theorem says you should have 5 terms less this one-dimensional ratio that's appearing. You should have 4 independent terms remaining. What the Buckingham pi analysis can't anticipate, however, is the additive nature of a couple of these stiffnesses and how the horizontal stiffnesses tend to add together. So although we've accounted for the way that the variables multiply together in clusters, we haven't accounted yet for the way that the stiffnesses that they sum and appear in sums. That's pretty hard to get out of a Buckingham pi analysis. Now I'm going to use some trickery, and there's not much generality in this. I'm going to now account for the summation property of the variables in the horizontal and vertical dimension by adding up the stiffnesses in those two directions and claiming then you only have one stiffness horizontal and one vertical. When you do that, the Buckingham pi theory would say that you only had two independent variables, and in this case then you could solve for one in terms of the other. Now, when we go back to the dimensional form of our equation, though, we still have apparently more than that. But what I'm going to do is use what's called static condensation, which we'll talk about later. And what that means is that you solve for the rotation u6 in terms of the other variables and eliminate it. We're going to get into that more seriously later on, but it gives a ratio as shown here and effectively eliminates one of the variables. So we'll use that static exact relation to reduce the problem a little further, getting rid of the rotation u6. There was no mass term associated with u6, and so it was relatively easy to uncouple. Then at this point, if we assume harmonic motion and non-dimensionalize, this intermediate equation here turns into this one, and now we're starting to get some real clustering of terms, and notice you've got this quantity out front appearing in the eigenvalue location. You've got this quantity appearing over here as a stiffness term. We've fortunately arrived at a mass matrix, which is a unit diagonal matrix, and this is more simplification than we could have hoped for, and certainly goes beyond the Buckingham pi theorem. It turns out we have two equations that only involve two non-dimensional ratios. And furthermore, those equations uncouple. So we get the chance again to solve for the eigenpairs for the first frequency and the second frequency. And when we do that, we find that omega 1 is this ratio of the K1 stiffness plus the linear spring stiffness K over the mass. If you think about that, that is a pure axial motion of the cantilever beam with the spring opposing the horizontal motion. So it's a rather pure mode that we might have guessed if we knew that the rod didn't couple into that. The second motion is actually the vertical motion, which adds the stiffness in bending, kind of a shearing force developed at the tip of the beam by the beam and the motion of the mass, and then the rod acting to prevent the motion. So again, you have the ratio of a sum of some stiffnesses over the mass. And those are the two frequencies. Now, someone who was really physically intuitive might have looked at this system at the outset and have seen that those two motions were so different that they would uncouple. But that's not clear. You really, I wouldn't have hoped that anyone in the viewing audience would have come up with this simplified uncoupled solution intuitively. Sometimes in an exam, though, we find people in a desperation will make such an approximation, and it turns out to be almost a stroke of genius, and I always appreciate that. That happens often, that people, when they're in a bind, will suddenly cut through all the nonsense and make a strong physical approximation. And as long as it doesn't throw the baby out with the wash, I usually appreciate that. Well, that's the end of this problem session.